Hello, everyone. I am Sunandita Patra from JP Morgan AI Research. I will be presenting our paper on FinRDDL, which explores whether AI planning can be used to solve quantitative finance problems. This is a joint work with several other researchers at JP Morgan. I would love to be there in person, but I am unable to travel due to visa issues in USA. So one thing I should stress is that all opinions in this talk are my own and does not reflect the opinions of JP Morgan in any way. So let us start with discussing the problem that we are targeting. So we will be focused in this talk on the problem of multi-period asset allocation. So what this problem involves is deciding the optimal set of weights of financial assets to include in a portfolio in each investment period. For example, in this pie chart, we have four assets, A, B, C, and D, and each color denotes each asset and how much of the portfolio that particular asset occupies. For example, at t equal to 0, A is at 58%, and similarly B, C, and D are at their own ratio of the portfolio. Then at a rebalancing period, which depends on the user, in this example, it is 30 days, the weights of the portfolio may change, and each asset will have a new weight. Similarly, at t equal to 60, t equal to 90, t equal to 120, the weights of the portfolio are revised so that to accomplish a particular objective. For example, you want to maximize the return of a portfolio. So if we use some mathematical notation, then if we say that the asset weight at time t is WT, then this is a vector where each term denotes the weight of an individual asset from 1 to n, where n is the number of assets in the portfolio. And the sum of all the weights of the assets at any time should be equal to 1, because the whole um, budget of the portfolio is distributed among the different assets. Now, if you want to maximize the return, then you should have some way to estimate the return at any particular time. So in this case, we denote the return using the symbol rho. So the return estimated at any time t is the weighted sum of the returns of the different assets at that time. And this is just an estimate. So you can use different formulas to do this estimation. For example, you can do log return, simple return, gross returns, and there are several sophisticated formulations of returns. And one critical thing I would say at this point is if they can be linearly summed to calculate the return of the portfolio, then that is a good property to have. That's why the log return was developed, keeping this in mind. And um, once we have some estimation of the return, one key property is that to estimate the return in a future time. For example, when you're at t equal to 0, then if you want to estimate the return at t equal to 60, it will be some model that you use to do this estimation. So that model comes with a risk, right? Because if we are solving this problem in hindsight, we would know that, okay, what's the exact price at a particular time, but we don't know that. So we are looking into the future. So there's a certain risk associated with the estimation of the return. So we would also want to minimize the risk. So along with maximizing the return, we want to minimize the risk of the portfolio as well. And finally, we want to minimize the transaction costs, because when we are changing a particular asset, for example, from t equal to 30 to 60, the weight of asset A changes from 57% to 29%. So this change would incur a transaction cost that the user needs to pay to the portfolio manager. So you would also want to reduce that cost for the different reallocation steps you are taking, because if you're paying a lot to the portfolio manager, that would usually discourage the user to change the portfolio. And in general, if you are suggesting a user to change the portfolio a lot, then they might be not comfortable with that, because people in general want stability in their portfolios, right? So that's something which is another target that we also want to minimize the transaction costs. Now, once we have understood the problem of multi-period asset allocation, why do we want to use planning to solve this? So one thing that you have already noticed is that it is a sequential decision-making problem. So we are looking for a plan, and we want to, because we want to decide the sequence of asset weights for each period. So at each period, this will be kind of the actions in the plan that will be the weights that we want to find. However, why have people not done it? What are the challenges? So the first challenge is that the search space is continuous, because the price of the assets, the weight of the assets, they are all real numbers, and finding optimal plans is known to be very hard in this search space. And the second challenge is, which makes the problem of continuous space even worse, is that the environment is highly dynamic with exogenous events happening all the time in the market, right? And so in this case, it's extremely difficult for planning models to accurately predict the next states and outcomes of the actions that the user is supposed to take. So this is where quantitative finance model can be useful a lot, because there has been several years of research to develop statistical models to predict the asset prices, which can handle dynamic events and also different kinds of unexpected exogenous events that are happening in the financial markets. So our solution, which can handle both continuous search space and also a dynamic environment, is to use a planning language called RDDL, which allows for concurrent actions to have conflicting effects depending on how the market is changing. And it can also incorporate different statistical models to predict the asset prices evolution over time using conditional and probabilistic state transition functions. So both of these challenges can be overcome using the RDDL planning language. Now let us dive into the RDDL domain for multi-period asset allocation. So the domain will have 5 key components: state variables, actions, the reward function, the transition model, and the problem. So starting with the state variables, it will have the weight of the asset that are in the portfolio. So each asset will have a weight variable associated with it. So if there are n assets, there will be n variables with the weight of each of them. And the price of the asset, similarly for each asset, there will be an individual price. Both of them are state fluent. So everything in RDDL is fluent. So that's a basic unit of RDDL, you can say. And the second term here would be the type. So weight and price both are real numbers. And finally, the day is also a state variable, because only if the day is a multiple of the reallocation or rebalancing period of the portfolio, then only you are allowed to change the asset. So that's why we need the day also as a part of the state. The second, going into the actions. So the action here is very simple. Action would be that what weight you want to set the asset. So at every rebalancing period, whatever set weight is assigned to a particular asset, that would be the uh, indicator of what should be the weight of the asset in the next period. So this is since this is the action, it's called action fluent. So each variable also has like a default value which needs to be set in the domain. The third one is the reward function. So the reward function is the objective that you want to maximize. So it can be a combination of the expected return and also the risk and transaction cost. The risk of the asset is the associated risk of that particular asset. Each asset has one risk variable. Then there are two scaling hyperparameters, alpha risk and alpha transaction cost, which is used to weigh the return, the risk, and transaction cost. Because when we sum all of them with a negative sign for the risk and the transaction cost, because we are minimizing these two, we might want to scale them because they may not be directly comparable, and some of the values might be very low compared to the others. So to overcome such scenarios, we have introduced some scaling factors to combine them. So this is one way of doing it. I must highlight that if the reward can have multiple components, that would be like the most optimal solution. But since in RDDL the reward has to be like one scalar term, that's why we have chosen to combine the rewards linearly. And this is a point of discussion if we have time later. The fourth item is the transition model, which describes how the state evolves from one period to the next based on the actions taken and also the dynamic environment that currently the market is in. So here in this RDDL domain we have developed, we have the weight of an asset evolving only when the day is a multiple of the reallocation period, depending on what the weight is set by the action in the RDDL model. And we also have the price that is evolving here. You can use any model where the price can be expressed as a function of the current state variables. So here the price in the next state. So yeah, this I should stress that the next state variables are denoted using the single quotation marks, like weight with the quotation mark on top is the next weight in the next state, and similarly the price with a single quotation mark on the top is the price of the asset in the next state, is a function of the mean, which is a parameter associated with the asset, the risk, and times the normal distribution uh, itself. So the day is very simple, it's just the next day. The fourth parameter of the RDDL is the problem. So the problem describes the initial state and the initial parameters. For example, the initial set of weights of two assets. If there are two assets in the portfolio, both their weight and the starting prices. The horizon here in this case, it would be, in this example, it's 300. So now that we have our RDDL model, we did a set of preliminary experiments where we compare 4 different acting strategies with 2 assets in the portfolio. So the 4 strategies that we are comparing are the uniform, the greedy Markowitz, the mixed integer quadratic programming, the Monte Carlo research, which uses the RDDL model. So the uniform strategy equally distributes the portfolio among the equal assets. The greedy Markowitz, it does mean variance optimization only for the current period. So it's like whenever you are at a particular period, it would do mean variance optimization in that period only. So comparing all the different actors, we see that the best performing are the mixed integer quadratic programming, followed by the MCTS actor in terms of the total cumulative total cumulative reward achieved for a horizon with 300 days. And the uniform, as we would expect, is the worst performing one. And greedy Markowitz is somewhere in the middle. So along with the total cumulative reward, one thing we should also observe is the asset weights in the portfolio. So as you may recall, that we don't want the portfolio to jump around a lot. So this is where the MCTS with the RDDL is performing the best, because as you can see from the different jumps in the asset weights, the MCTS one is performing the lowest number of jumps. So finally, we are concluding with a few points of discussion, if we have time for, is can we support multidimensional rewards? Like instead of combining risk, return, and the transaction cost, can we use, instead of combining them into like one linear term, can we use multi-objective planning algorithms? Second one is, can we improve the Monte Carlo research approach with the RDDL to modify the reward function to include risk matrix and also optimize the risk return trade-off within the MCTS approach. Finally, can we do an integration of planning and acting in this setup? That is, once the portfolio asset weights are decided, can we also simulate the trade execution to simulate the different uncertainties that are associated with the execution and of the trade itself into the problem of asset allocation? Like, can we solve the two problems together?